Chapter 13, we're going to look at the properties of solutions. So we're going to be talking about concentration, a little bit with some intermolecular forces, things that are going to affect solubility. Remember, solubility involves forming a precipitate, as well as what are called colligative properties. Now, your lab for this unit involves colligative properties, and here are some calculations involving colligative properties. You know we can't get away from that. Now, something to keep in mind, this chapter does tend to be easier for our Chem 1 students, and that is so that you can spend some time studying for the final exam. Now, we have several different types of solutions. Remember that a solution is a homogeneous mixture of two or more substances. So a homogeneous mixture is you can't see the parts. Remember, a chocolate chip cookie is a heterogeneous mixture. You can see the chocolate chips versus the cookie, but a homogeneous mixture is more like a cup of coffee. You can't tell if there's sugar in that coffee or not. Now, we can have any phase of matter for the solute, and we can have any phase of matter for the solvent. So we can have homogeneous mixtures of many different types of solutions. So a solution can be classified by the amount of solute that is dissolved. So an unsaturated solution contains less solute than the solvent has capacity to dissolve. So for example, 1 teaspoon of sugar in my large cup of coffee would be an unsaturated solution. So you would take the solid, put it into the solvent, and then after mixing, you can't tell that there's solute in the solution. It just looks like the solvent. You can also have a saturated solution. Now, this is one that contains the maximum amount of solute that will dissolve in a solvent at a specific temperature. So my husband's coffee is closer to a saturated solution of sugar in coffee. He likes an awful lot more sugar than I do. So this is more solute into the solvent, and then you form any additional solute added forms a layer of solute on the bottom because the solvent just can't handle any more solute in it. Then we have what's called a supersaturated solution. This contains more dissolved solute than is present in a saturated solution, and it's usually an unstable solution. And there is a lab out there, or a demonstration out there, and it's called making hot ice or something like that. It's actually forming sodium acetate. And the idea is you make a supersaturated solution. And then when you put one crystal into the supersaturated solution, because now this solvent holds more solute than it really wants, that acts as a nucleation point. And then you will get the crystal growth happens very quickly, and it's almost immediate. You can watch these crystals grow from this supersaturated solution, and it becomes hard with crystals. It's really amazing to watch. Now, the act of solvation is when solute molecules are separated from one another and surrounded by solvent molecules. So solvation depends on the solute-solute interactions. So we have I'm just going to use sodium and chloride. So we have what we learned in the previous chapter. We have these unit cells, right, of sodium chloride. So here we have solute-solute interactions. And then our solvent comes in, and then we have an interaction between the solvent and the solute. I'm going to draw my water molecule going this way. And that's an H, it's not an I. And then we have solute-solvent interactions. So we have all of these interactions here. And the solvation will occur, let's see if I can change a couple of colors. Solvation will occur when this solvent to solute overwhelms solute to solute. Now, components of a mixture can have different properties, and there are a lot of different intermolecular forces to consider. For example, you can have ion dipole intermolecular forces, dipole-induced dipole forces and ion-induced dipole. And basically what we're looking for is the strength of the intermolecular forces between the solute and the solvent. It takes energy to separate a solute. It takes energy to separate a solvent. And remember Hess's law, the sum of the parts, we also have an energy associated with the creation of a solution. So the actual energy of creating this solution is the sum of the parts, but look at the energy of creating the solution itself. So remember the delta H of the solution will be additive for each of the steps, just as Hess's law states, but creating the solution is typically going to be a lower energy system, so delta H is going to be negative. Now the entropy of a system, before we've been talking about enthalpy, the entropy of a system measures how dispersed or spread out the energy is. Entropy is called the chaos function. So we're measuring the level of chaos. There's a natural tendency for a system to be dispersed or to be chaotic or to be disordered. It's the disorder. It's the measure of disorder rather than order. So when we have our separate gases, there's a natural tendency for our gases to spread out and become a mixture. Now with a solution, you need to remember that like dissolves like. Remember your polarity stuff when you're looking at solvents and solutes. So two nonpolar compounds like carbon tetrachloride and benzene, they will dissolve in one another, or they will be soluble. Here we have methanol and ethanol. These are both polar because of the lone pairs on the oxygens and the OH bond here. So because these are both polar, they are miscible. Two liquids are said to be miscible if they are completely soluble in each other in all proportions. So ethanol and methanol are miscible. So let's work this example. Determine for each solute whether solubility will be greater in water, remember water is polar, or benzene, which is nonpolar. So we need to consider the structure of each. If we have bromine, remember bromine is going to kind of look like this with all its electrons. This is a nonpolar molecule because it is a homonuclear diatomic molecule and it is nonpolar, then it will be more soluble in benzene. B, we have sodium iodide, NaI. The Lewis structure looks something like this. Remember, we're making a positive and a negative. We have an ionic compound. That ionic compound is polar, therefore it will be more soluble in water. For C, we have carbon tetrachloride. Carbon tetrachloride looks something like this, and I'm going to leave off the extra electrons here. Now I'm going to put this on a wedge. That means this one needs to be on a dash because that indicates this is coming out towards me and this one is going behind. This is a nonpolar molecule, therefore it will be more soluble in benzene than in water. And D, we have formaldehyde. Formaldehyde looks like this. It is a polar molecule, therefore it is more soluble in water. Now, when we're talking about solutions, we talk about them in terms of their concentration, and that gives us the amount of solute relative to the volume of solution or the amount of solvent in a solution. And that's called the concentration. What we're talking about is how much solute per solvent. We have a couple different ways to talk about concentration. We have molarity, which is moles of solute divided by liters of solution, and we've mentioned that before in this class. We have mole fraction, which is the moles of some component A divided by the sum of the moles of all components. Again, we've talked about that already in here. And then we have what's called molality. Molality is very common in your biological sciences. So those of you who are going on to things that are more biologically oriented, including the health sciences, you might deal with molality more. At least when I was in school, that was the case. It might not be the case anymore because I'm getting old. So molality is the moles of solute divided by the mass of the solvent in kilograms. So molality's units are moles per kilogram. And remember, this is kilograms of solvent, not of the solution. So percent mass is another way we can talk about concentration. And percent mass means parts per hundred. So we're looking at the mass of the solute again, divided by the total mass of the solution, which is found by the mass of the solute plus the mass of the solvent. So we have these two masses in their mass ratio, and then we're going to multiply by 100. Now, if you're going to do parts per thousand, which is commonly abbreviated PPT, or parts per million, which is ppm, or parts per billion, which is ppb, then you would change this multiplier here. In mass percent, our multiplier is 100. In parts per thousand, you would change that to 1,000. And then parts per million, of course, would follow. You change that to a million. But it's still mass of the solute divided by the total mass of the solution. So a solution that is made by dissolving 170.1 grams of glucose in enough water to make a liter, we have the density. So let's express the concentration in all three of these units: molality, percent by mass, and parts per million. Well, for molality, I need moles. And remember, I keep saying 99% of the time in here, you see grams, we're going to need to convert it to moles. Well, this is the chapter where you may or may not. So this is the chapter where you really need to pay attention to that. So I'm going to convert that to moles using the molar mass of glucose, 180.2 grams per mole of glucose, and I get 0.9440 moles of glucose. Now for molality, remember molality equals moles of the solute divided by the kilograms of the solvent. So I have moles of my solute here. I need the mass of my solvent. So I'm going to take the 1 liter, because it says I have 1 liter, and I'm going to multiply it by the density. So I'm going to have my 1,000 milliliters multiplied by my density, and that equals the mass of my solvent, of my solute, or my solution. Oh my goodness, that's the mass of my solution. Now I have to take out the mass of my solute because I need kilograms of solvent, and I get 0.892 kilograms of water. So this is 892 grams of water. We need kilograms. So this is going to be, remember, just solvent, 0.892 kilograms. Moles of my solute, 0.9440 moles. So the molality of this solution is 1.06, kind of a scripty m, lowercase m. B, percent by mass. I need the grams of my solute, which is given to me, 170.1 grams, divided by the mass of the solution. So here I'm looking for solute plus solvent. Mass of the solution is given right here, 1062 grams. I'm looking percent mass, so I need to multiply by 100, and I get 16.02%. For C, I'm asked to find parts per million, and it starts the same way as percent mass. 170.1 grams, because that is the mass of my solute, divided by the mass of my solution, 1062, which I found up here. This time multiplied by a million, because I'm looking for parts per million. So in this case, I have 1.602. I'm going to use significant digits or scientific notation, times 10 to the 5, and that's ppm. Now, when we use which concentration unit is really going to be based on the experiment itself. So pay attention. When we use molarity, we're usually doing titration or gravimetric analysis, and really molarity is the one we use the most of the time in a chemistry lab. Mole fraction is best for something like gases or vapor pressure. Molality and percent by mass is going to be something that's independent of temperature. So for example, if we have isopropyl alcohol, well, rubbing alcohol, which is isopropyl alcohol in water, then we're looking at 70% isopropyl alcohol by mass. Here's the density. And we're asked to express the concentration of rubbing alcohol in both molarity and molality. Well, in this case, I'm going to make up that we have 1 liter. So for molarity, I need moles of solute and liters of solution. And for molality, I need moles of solute per kilogram of solvent. So I'm going to start by saying if I have 1 liter of solution, then how much isopropyl alcohol do I have? What is the mass? What is the moles? So if I have 1 liter and I have my 1 liter, I'm going to say I have 1,000 milliliters. It has a density of 0.79 grams per milliliter. So in 1 liter, that's the mass of one liter of isopropyl alcohol or rubbing alcohol, but it's only 70% isopropyl alcohol. So it is 70 for every 100 grams of solution, I have 70 grams of isopropyl alcohol, IPA. Now, the molar mass of isopropyl alcohol is 60.09 grams per mole. So doing this calculation, I find that I have 9.20 moles of isopropyl alcohol in 1 liter. So 9.20 moles of IPA in 1 liter of rubbing alcohol is a molarity of 9.20 capital M molar. For B, I still have my 9.20 moles of isopropyl alcohol, but now I need to know the mass of my solvent. Well, I know my solution is equal to, when I'm talking about the mass of solution equals the mass of my solute plus the mass of my solvent. Well, the mass of my solution I know, and I know that because of my density here. So 1 liter of solution, because I just picked 1 liter for ease, is 790 grams. I know the mass of my solute because I calculated that if I take this, the mole equation and take it back a step, I have 553 grams of my solute. So what I don't know is what's left, and that's the mass of my solvent. Well, that is 237 grams or 0.237 kilograms. So when I use this information in order to calculate molality, I get 39 M molality, 39 molal. We first talked about solubility when we were talking about aqueous reactions. And what we found in those reactions was we were predicting whether we would form a precipitate. Well, now we have factors that will affect that solubility, and one of those factors is temperature. For most ionic solids, as you increase the temperature, you increase the solubility. Notice how temperature is increasing here and solubility is increasing here. Now, that's not the case for everything. There's always an exception to our rule. And look, here we have sodium chloride. And sodium chloride has the same solubility independent of temperature. But look at all of these, especially something like potassium bromide, given up here. As you increase the temperature, you increase the number of grams of solute able to be dissolved in 100 milliliters of water. Pressure also influences solubility, but it influences the solubility of a gas. For example, the solubility of a gas in a liquid is proportional to the pressure of the gas over a solution. This is why soda is bottled with what's called a headspace of gas. So you have your bottle, and I'm not an artist, don't make fun of me. And here's our cap. You have this area because it's not filled all the way to the top. This area right here between the top and the liquid is called the headspace. And when they bottle these sodas and other carbonated beverages, they always have a headspace, and they will pump in carbon dioxide because they want that carbon dioxide to be soluble in that liquid. So the more pressure here, then the more gas is soluble in that liquid. Now C in this equation is the molar concentration. So we're talking about capital M molarity, moles per liter. K is a constant and P is the pressure. And this is Henry's law. So if we're going to calculate the concentration of carbon dioxide in a soft drink, bottled under this partial pressure at 25 degrees Celsius, before the bottle is open first, let's just start there. So if we're going to calculate the concentration, then we need C, the molar, times K, P. Well, C is the molar concentration, and Henry's law constant for carbon dioxide in water is known, and here it is. It's given to us right here. So that's our K value. So C equals 3.1 times 10 to the negative 2 moles per liters atmospheres. Notice how we're looking for moles per liter, so we must have to multiply this by a pressure. And in this case, the pressure is 5.0 atmospheres. Notice how our units match and cancel out. So 3.1 times 10 to the negative 2 times 5 equals a C, or concentration, of 1.6 times 10 to the negative 1 capital M molarity. B, after the soda has gone flat at 25 degrees Celsius. Well, after the soda has gone flat, then we're assuming that the partial pressure, again given to us, is 0.0003 atmospheres. So C equals, again, our 3.1 this time multiplied by the second partial pressure. So when it has gone flat, it has a concentration of 9 times 10 to the negative 6 moles per liter, or capital M moles. You can see it's by a factor of 5, 10 to the fifth difference here. Now, when we talk about solutions, we also need to talk about colligative properties, and your lab involves colligative properties. Colligative properties are dependent on the number of solute particles in solution, not on what those solute particles are, just how many there are. Now, colligative properties include vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. Usually we note boiling point elevation as BP up arrow and freezing point depression as FP down arrow. Now, Raoult's law will state that a partial pressure of a solvent over a solution is given by the vapor pressure of the pure solvent times the mole fraction. Well, okay, in letters and numbers, that's P1 equals the mole fraction 1, and then P naught 1, where P1 is the partial pressure of the solvent, P1 naught is the vapor pressure of the pure solvent, and X1 is the mole fraction. Well, you got to know that then the change in partial pressure would be equal to this change here with the second mole fraction of the solute. So to put that in, we will put that in perspective with some problem solving. Don't worry. Just understand what Raoult's law states, and we'll work the problems from there. If components of a solution are called volatile, volatile is a key word you need to know, the vapor pressure is the sum of the individual partial pressures. So The vapor pressure, P total, will be the sum of the partial pressures, PA plus PB. So if we have benzene and toluene, then we have our mole fraction of benzene, and here's the pressure. Here's the total pressure here. And you can see how the total pressure is an addition of both of these lines. Now, an ideal solution will obey Raoult's law. So if we're going to calculate the vapor pressure of water over a solution made by dissolving 225 grams of glucose in 575 grams of water, then what we need to do is first start with the mole fraction of water. Remember, in order to calculate the mole fraction of water, we will need moles of water divided by total moles. So we have 225 grams of glucose. We need grams of glucose. Remember, 99% of the time, you're going to have to convert grams into moles. Remember, glucose is 180.2 grams per mole. So we can calculate our moles of glucose as 1.25 moles. And then our moles of water, we have 575 grams of water. And water is 18.02 grams. So we have 31.9 moles of water. So our total moles then is 1.25 plus 31.9 moles of water in the numerator, divided by 1.25 plus 31.9, and I get a mole fraction of water of 0.962. Now we're not done, because the pressure of water will be equal to the mole fraction of water times the vapor pressure of water. Now the vapor pressure of water is given to us right here, so we don't have to do a whole lot more than put 0.962 times 42.2 millimeters of mercury. So we get a pressure of water, vapor pressure of water of 40.6 millimeters of mercury. Now we also have our boiling point elevation. There is a thing that has been floating around for as long as I can remember, that you put salt in water to boil pasta because it raises the temperature of the boiling water. And that's actually incorrect, because the amount of salt you need in order to increase the boiling point of water, anything considerable, is so much salt that it makes your pasta really gross. But we can change the boiling point of water, of a pure solvent, not just water, but any pure solvent, by adding a solute. And it doesn't matter what that solute is, it's how many particles we have. Now the change in boiling point here will be equal to a boiling point elevation constant, which should be given to you, times the molality. Remember, molality is moles of solute per kilogram of solvent. So solutions, freezing point depression is found similarly, where we have our Kf, or freezing point depression constant, again given to you, times the molality. Now both boiling point elevation and freezing point depression then are based on how many moles of solute we have per kilogram of solvent. So with water, now the freezing point depression is what is used in the wintertime in cold areas when the Department of Transportation either spreads a brine solution or some sort of salt solution. And remember, salt is a chemical term, not necessarily just NaCl. A lot of times when salt solution is spread on roads, it's a magnesium salt of some sort with some counter ion, or a calcium solution with a counter ion of some sort. So these solutions being spread on roadways decreases the freezing point of water, and that's beneficial to those of us who wish to travel on the roads. Now, ethylene glycol is a common auto antifreeze, and it's water soluble and it's fairly non-volatile. So we are asked to calculate the freezing point and the boiling point that contains 685 grams of ethylene glycol in 2,075 grams of water. Well, in order to calculate the freezing point, remember our freezing point depression will be equal to some constant times the molality. Well, that constant is going to be 1.86 degrees Celsius per molal unit. And I found that on the previous, right here, on the table. You do not need to memorize it. And the molality then in this case is going to be moles of ethylene glycol. And I'm just going to do that all right here. So 685 grams of ethylene glycol times the molar mass, or divided by the molar mass, depending on how you want to look at it, which is 62.07 grams. So that's moles of my solvent divided by the kilograms of my solvent, so 2.075 kilograms of water. So I get a freezing point depression then equal to 9.89 degrees Celsius. Now remember, that is the depression. That's not the freezing point. The freezing point itself would be the normal freezing point of the solvent, 0 degrees, minus then the amount I'm being depressed. So then this would be a negative 9.89 degrees Celsius would be the new freezing point. So for B, if we're going to calculate the boiling point of this solution, then remember my T delta T B is going to be equal to KB times M, the molality. Go back to my table. KB is 0.52. So 0.52, and that the units for that are degrees Celsius per molal unit. And that is, well, all this stuff worked out to like 5.32 molal. So the boiling point change is 2.8 degrees Celsius. My normal boiling point, remember the new boiling point of solution will be my normal boiling point plus this, 2.8 degrees Celsius. So my new boiling point is 102.8 degrees Celsius. So colligative properties will extend the liquid range of a solvent. So here we have a solute added, and our liquid range then increases by a span of nearly 12 degrees. Because instead of going from 0 to 100, now I can go from negative 9.89 to 102.8 before I change phases. The last of our colligative properties that we're going to look at is called osmotic pressure. Now, osmosis is a selective passage of solvent molecules across a porous membrane. You can think of this porous membrane as something like a cell wall, or the shell of an egg, or the membrane inside the shell of an egg. And this will go from a more dilute solution to a more concentrated one. So it's the solvent that moves, not the solute. The solvent moves. So here's more dilute. I can't spell dilute. There we go. And this one's more concentrated. So this one then will travel to the more concentrated in order to try to dilute all of that solute down, in order to put more solvent in there. And then the osmotic pressure itself is the pressure that would have to be applied in order to prevent that from happening. Now that can also be measured as the difference of heights if you have the appropriate solution. So it's the pressure that's either exerted here or the pressure that's exerted here to prevent it from happening. So the osmotic pressure of a solution required to stop osmosis can be produced in an equation. Pi equals capital M, molarity, R is our gas constant, T, temperature. Now in this case, our gas constant is actually going to be the gas constant, 0.08206 liters atmospheres mole Kelvin. This is the one that we used in our gases chapter. Now again, T must be in Kelvin for these equations. Remember, that's because our R has Kelvin in the units. Now, an electrolyte solution will undergo dissociation when dissolved in water. We have our weak electrolytes and our strong electrolytes, and we talked about that when we talked about ionic compounds. The Van 't Hoff factor, which is symbolized as an I, accounts for this effect. So I is the actual number of particles in solution after dissociation. So NaCl dissociates into sodium and chloride, that's 2 particles. And something like, how about calcium chloride actually would dissolve into 3 particles. See how that works? So that's the actual number of particles, and then the number of formula units initially dissolved in solution. So the freezing point change as well as the boiling point change is basically the same as before, but then we have this Van 't Hoff factor, the I value. Now pi then, the osmotic pressure, is also dependent on the number of particles. So those numbers of particles become very important. So calcium chloride could produce 3 particles if it was to break apart, or magnesium chloride for that matter, or sodium sulfide, something like that. Now the Van 't Hoff factor is 1 for all non-electrolytes. So all of your covalently bonded compounds, you have 1 particle dissolved. When it's solid and then it becomes aqueous, something like glucose would be a non-electrolyte. Now for strong electrolytes, the I will be equal to the number of ions. This is the example I gave you. There are 2 particles dissolved. And here for sodium sulfate, here we have 3 particles dissolved. I is 3. Now it's usually smaller than predicted because of the formation of ion pairs. Now an ion pair is made up of 1 or more cations and 1 or more anions that will be held together by electrostatic forces. So notice, although hydrochloric acid, HCl, has a calculated I value of 2 because it breaks up as hydrogen and a chloride, but it's actually measured at 1.9. So the I's that are measured will either be given to you or you will have a table of some sort. You are not expected to memorize those. Now concentration also has an effect on the Van 't Hoff factor, on the I, and the concentration effect is seen here with sodium chloride. As you decrease the concentration, here's the molal factor, here's the molality here, you actually increase the number of particles. So the stronger, the more concentrated the solution, the more ion pairs you will form. So if we're going to work this example, the osmotic pressure of a 0.01 molar potassium iodide solution at 25 degrees Celsius is this pressure, 0.465 atmospheres. So we're told the osmotic pressure is 0.465 atmospheres. Determine the experiment Van 't Hoff factor. Well, pi equals I, capital M, RT. So I'm going to fill in the numbers I know. I'm going to bring my MRT to the other side. The molarity is given to me, 0.0100 capital M molarity. R, I'm going to leave the units off just for brevity. And T is given to me at 25 degrees Celsius, but I know that has to be in Kelvin, so I'm going to call it 298.15. So I do that calculation and I find that I is equal to 1.90. So the experimental Van 't Hoff factor for this particular experiment is 1.90. Now, when we do calculations concerning colligative properties, we might need to know the percent dissociation or the percentage of dissolved molecules or formula units if we're talking about ionic compounds that separate into ions. And this can be found using our colligative properties. Now remember that strong electrolytes should, the operative word here is should, have complete or 100% dissociation. Experimentally determined Van Hoff factors indicate that's not always the case, but percent dissociation of a strong electrolyte is more complete at lower concentration, and we saw that with that table. Percent ionization of weak electrolytes is also dependent on concentration. So to illustrate this, we'll work this example. Quinine was the first drug widely used to treat malaria. It remains the treatment of choice for severe cases, and a solution is prepared by dissolving 10 grams of quinine in 50 milliliters of ethanol. And it has this freezing point. And this freezing point below that, a pure ethanol. So we're asked to determine the molar mass of quinine. We're given the density. And we're told that it's a non-electrolyte. So the I factor is going to be 1. Now, we are asked to find molar mass. That's our end game here. And molar mass, remember, is grams per mole. I have grams here. Now let's figure out the moles. So what I have and what I know is that my freezing point depression is 1.55 degrees Celsius. And I know that that change in TF is equal to M molality times the KF. Now I've looked up that KF, and that KF, hang on, I'm going to put this down here. The KF is actually 1.99 degrees Celsius per molal unit. So if I'm looking for my molality here, then my M equals 1.55 degrees Celsius divided by my KF, 1.99, and those units are degrees Celsius per molal unit. So M is then equal to 0.779 molal. Now remember, molal is moles of solute divided by kilograms of solvent. Now I'm going to determine the kilograms of solvent that I have. I have the density of ethanol here, and I was told 50 milliliters. So I'm going to take those 50 milliliters, multiply it by the density, and convert that into kilograms, and I get the mass of my ethanol is 3.95 times 10 to the negative 2 kilograms. So now I can say that my moles of solute, if I rearrange that equation here, then my moles of solute will be 0.779 molal units divided by, or multiplied by, not divided by, multiplied by the kilograms of my solvent, 3.95 times 10 to the negative 2 kilograms. Because what I'm doing is I'm taking this equation here and multiplying both sides by kilograms of solvent in order to get my moles of solute alone. And then I get 0.0308 moles of my solute now. So now I have grams and I have moles of solute. Remember, molar mass is grams per mole. So I'm going to take the grams I started with, divided by the moles I calculated, and I get 325 grams per mole. Working this example, if we have a solution that is prepared by dissolving 50 grams of hemoglobin, so there's our solute, in enough water to make a 1 liter of solution, that's our solution volume, not our solvent. We have an osmotic pressure that is measured, and our osmotic pressure is measured to be 14.3 millimeters of mercury at this temperature, which we have to convert, so I'll just do that to 98.15 Kelvin. We're asked to calculate the molar mass of hemoglobin. So remember, our end game is grams per mole. We were given grams here, so we need to convert, or we need to calculate our moles. Now we were given our osmotic pressure in millimeters of mercury. We need to convert that to atmospheres, and we need to convert that to atmospheres because our R value is in atmospheres. So when I do that, I get 1.88 times 10 to the negative 2 atmospheres. Now remember that pi equals mRT. So we have our m value, which is what we're looking for. So I'll rearrange. So m equals pi over RT. So pi was calculated in atmospheres, 1.88 times 10 to the negative 2, divided by our R value, 0.08206. Remember that's liters atmospheres per mole Kelvin, times T, our Kelvin at 298. So we get a capital M molarity of 7.69 times 10 to the negative 4 capital M molarity. Now remember that capital M molarity is moles per liter. We have 1 liter of solution, therefore we have this many moles. We were given 50.0 grams. We have 7.69 times 10 to the negative 4 moles. So I get 6.50 times 10 to the 4th grams per mole. So that is the molar mass of hemoglobin. Now again, this is moles per liter. We have 1 liter, so this is also equal to the value of moles. Here's another example, a solution that is 0.100 molar in hydrofluoric acid. It has an osmotic pressure, so we're given our pi value of 2.64. We have our T value of 298 Kelvin. Calculate the percent ionization of HF at this concentration. Well, the first thing I'm going to do is find the concentration of dissolved particles, and that's going to be found by pi equals mRT. So in this case, the M, the capital M, is not what we're given to us. This is the M of dissolved particles. So if I rearrange, M equals pi over RT, then I can plug in my numbers and calculate. So I have 2.64 atmospheres divided by the product of 0.08206. Remember that's liters atmospheres per mole Kelvin times T temperature 298 K. Then I end up with 0.108 capital M, that's moles per liter. It might be easier if I write out moles per liter rather than give you the capital M. So the concentration of the dissolved particles is 0.108 moles per liter. In this case, the difference between the percent of the difference in the concentration of particles that we calculate and the concentration of our beginning solution, that difference is the number of particles that we have, the number of ions. So that difference divided by what we've started with times 100 equals the percent ionization. Now again, the difference in the concentration of particles we calculated and what we started with is the number of particles in solution. Now, the last type of solution we will talk about are called colloids, and a colloid is a dispersion of particles of something throughout another substance. Colloid particles are going to be larger than normal solute molecules. Milk is a colloidal dispersion. We can have aerosols, we can have foams, we can have emulsions. These are all colloid mixtures, or we could have what are called sols and gels. So if we can have dispersing mediums as well as the dispersed phase of all different phases of matter. So if we have a gas as the dispersing medium, but liquid is the dispersed phase, we have an aerosol. Solid is the same way. These are like spray paints. Liquid as the dispersing medium, but gas as the dispersed phase, that would be a foam, something like whipped cream, or there's a foam insulation stuff. It's called great stuff. This is a great example of that. Now, colloids that have water as the dispersing medium can be categorized as what's called hydrophilic or hydrophobic. Philic is loving, phobic is fearing, hydro is water. Hydrophilic groups will stabilize the molecule in water. These are going to be your polar groups. Negative ions tend to be adsorbed onto the surfaces of hydrophobic colloids, and then you get a repulsion between like charges, and that prevents the aggregation. So you have this suspension rather than any of these colloidal particles aggregating and then falling out of solution as a precipitate. Now, hydrophobic colloids can be stabilized by the presence of hydrophilic groups. This is an example of this is actually a soap. This is sodium stearate. Here you have your polar end. So this is hydrophilic, and this is the hydrophobic tail. And what happens with soaps is, depending on the soil type, let's say it's an oil soil, then the hydrophilic tails will form what's called a micelle if I put the polar ends on it like this. So the hydrophilic ends surround this soil, this oil soil or hydrophobic soil, and then they can actually bring them into solution, into the water solution, to be essentially dissolved and carried away, because these polar parts here attach to the water molecule in whichever orientation, depending on the polar particle that we're talking about. This, of course, would be attracted to the H, and the O would be out here. Now, emulsification is the process of stabilizing a colloid that wouldn't otherwise stay dispersed. Emulsifiers are used in food a lot, something like soy lecithin, or sometimes pronounced licithin. It's something that's used, it's abundant in the majority of processed foods. So emulsification stabilizes something that otherwise would not stay dispersed. So oil in water, for example, can be emulsified. Mayonnaise is an emulsification. The oil in egg ends up being stabilized together so that it doesn't fall out or fall apart. Now in chapter 13, we have a lot of concepts and very little calculations here, and that's by design because you also need to prepare for your final exam. We have all of these, let's see, all of these definitions. There's a little bit with energy and entropy in solutions, but not much. Molarity and mole fraction, molality, percent mass. Here's where the majority of your calculations should come from. There will be some regarding colligative properties. Vapor pressure lowering, I like the boiling point, freezing point stuff more than I like vapor pressure lowering for calculations. I can't say that there isn't one on the quiz, in the quiz pool somewhere, but I like these better. Osmotic pressure, electrolyte solutions with the Van Hoff factor. Yeah, there's a couple of those, but really a lot of this chapter is going to be concepts and a lot of conceptual things with a lot of definitions. Now, if you have any questions regarding these topics or anything else with the class, please let me know.